So we are talking today about section 4.4, and what we're talking about are rational functions. And so rational functions are very simple. The book likes to use R of x, and I like P of x over Q of x. So a rational function is a ratio of polynomials, right? Where P and Q are polys, right? I should use capital letters there because I had capitals. So my P of x, my numerator and my denominator are both polynomials, and Q of x does not equal 0, right? So I can't divide by 0. So again, you're going to be graphing these right away, and we really want to be careful of multi-terms. So watch out for multi-term numerators and denominators, right? Watch out. Oops. Watch out for multi-term numerators and denominators. It's very easy to make a mistake in the calculator when you have a multi-term numerator and denominator. So for example, if R of x was something like x squared minus 1 over x squared minus 9, I would want to make sure that I'm wrapping these not in like a Mathers type way, but with parentheses, right? So I want to wrap the multi-term numerators and wrap the multi-term denominators before I would go to the calculator there, right, with my y1. So just be really careful about it. And then of course we want to be thinking about the standard form and the factored form. Right, so standard form would be my polynomial upstairs would be expanded all, and downstairs same thing. And then the factored form upstairs would be completely factored, right? So I might need synthetic division here, and the downstairs would be completely factored. And then we want to also think about the reduced form. So the reduced form kind of gives it's leading towards something called removable discontinuities. Discontinuities. So we know what it means to be discontinuous. There's a hole in the graph, right? Like a roller coaster, and you'd fall through, kind of thing. And so these removable ones, you can't tell there's a hole there when you look at the graph. But you have to think of that original domain. If you remember when we were dividing functions, we had to take the domain of the numerator, intersect with the domain of the denominator, and then include the domain of the new function as well, right? When we first did that at the very beginning of the, I think in chapter 2. So we got to kind of build up these processes and keep them all, right? So our first real question is, what's the domain? Maybe what's the range? Where are there vertical asymptotes? Where are there horizontal asymptotes? And then eventually, where are there oblique asymptotes? So our first kind of process here is domain, maybe range, HA and VA, right? Horizontal asymptotes, horizontal, vertical asymptotes. graph, and then possibly oblique asymptotes. In the past, I've always kind of skipped oblique asymptotes, but there's a bunch of them in the homework, so I'd rather just teach it to you because it's not difficult. When my numerator is of a higher degree than my denominator, then there's an asymptote. If it's 2 degrees higher or more, then there's an oblique asymptote. I'm sorry, no. If it's even 1 degree higher, there's an oblique asymptote. 2 degrees higher, there's a quadratic asymptote. 3 degrees higher, there's so et cetera, but I'll show you what I mean by that. I should be able to think of long-run behavior. This is just a kind of a checklist for me here. Short-run behavior. And I think that's it. So that's everything we're going to talk about in 4.4 and probably all we're going to talk about in 4.5 as well. So 4.4 starts a little bit easy, and then we get into some of these more complicated things into 4.5. What's the first thing you're going to do? Graph it. Be careful about multi-terms. What's the second thing you're going to do? Factor it, right? Then you're going to find domain. You're going to find range from the graph. You can't. I haven't taught you how to get range from a function yet. That's in chapter 5. And then vertical asymptotes, horizontal asymptotes, long-run behavior, short-run behavior. You're going to see all of that. I need to remind us of a couple of mother functions that are important because I'm going to really see in the short-run behavior piece these mother functions happening. So, of course, 1 over x and y equals 1 over x squared. These are the two I want us to really make sure we see. So 1 over x is this one, and 1 over x squared is this one, right? And of course, if I square something, all the negatives turn to positive, right? So you can see the relationship between 1 over x has got a positive side and a negative side, and 1 over x squared is going to make everything steeper, but put them both positive, right? You probably want to graph 1 over x squared, 1 over x cubed, 1 over x to the 4th, all in the same graph so you can see kind of what's happening as you increase that power, right? Okay, I think we're ready. We can look at a couple of problems in the homework. So this is from section 4.4. This is homework 17. Oops, access denied. I gotta log in again, sorry. 1 second. Homework 17. There we go. Oh, it looks like, how many students are we missing? Why are students missing class so much? I don't get it. I'm gonna take a quick attendance. Don't miss class. I know sometimes it's not in your control, but. All right, so here we start nice and simple. I've got my function 18x all over quantity x plus 10. You can see here I do have I have a downstairs 0, right? I have an upstairs 0, I have a downstairs 0. Oh yeah, I need intercepts too, right? But we're just talking about domain first. So 18x over x plus 10. So this is homework 17, which is 4.4, number 1. And we've got an R of x equal to 18x over x plus 10. So, I mean, they're only asking for domain right now, right? And so it's all about what x values are you not allowed to plug in, right? And so you've got a couple of rules. You can't divide by 0, and you can't take a even root of a negative, right? So the only possible one here is dividing by 0. So obviously x equals 10, sorry, negative 10, right, is not in the domain, right? And so the domain here of R is going to be minus infinity to negative 10 union negative 10 to infinity. I could also have just written that as all of the reals minus the singleton negative 10. But the book is usually asking for intervals most of the time. So right, this is in standard form, right? I would definitely have to wrap the downstairs if I'm going to graph this, right? So if I'm going to go to graph this, I see 18x divided by parenthesis x plus 10. And you're going to get pretty good at graphing these without anything, because now at negative 10, there can't be a point. So there's got to be some kind of line here. This is called a vertical asymptote. When the denominator equals 0, after reducing, so if I could cancel first, I don't have to think about this. But if my function is dividing by 0 after I've reduced my function, then I've got a vertical asymptote. I like to look at short-run behavior real quick here. So R of negative 10, this is Kuhar's short-run behavior trick. I'm going to plug in negative 10 where I can. I get 180, negative 180 over x plus 10. Notice I can plug it in upstairs, but I cannot plug it in downstairs. And so what do I get? Negative 180 over x plus 10. So the mother function is really looking like a negative 1 over x. So my mother is a negative 1 over x. So at the short run behavior, I'm going to see 1 over x, but switched, right? So 1 over x looks like this, and now it's because it's negative, I switch the two. And that's really a quick way for me to get a nice picture of this graph. I should probably get intercepts, right? At R of 0 is 0, so I know I hit a 0, 0, so I should have had that in there. And the long run behavior on this one is I let x go to infinity and see what happens, right? So as x goes to plus or minus infinity, 18x over x plus 10 behaves like 18x over x. So I like to think of x as money, okay? So if x is $1 million or $1 billion or a godzillion dollars, do I care about finding a $10 bill? If downstairs there, if I have a godzillion dollars, do I care about a $10 bill? No, probably blowing my nose with it, right? Probably using 50s or something, or hundreds. So in the long run, x plus 10 becomes its mother, it becomes x. And so then I could see that this becomes 18. And so there's a horizontal asymptote at 18. So short run behavior, long run behavior, vertical asymptotes, horizontal asymptotes, domain, intercepts, right? So that's what we have on our mind right now. And of course, put it in the graph and put it in the calculator, and you should see the same shape. How we doing? Can you tell I had a lot of sleep last night? It seems like I'm running.
So far, so good.
Okay, nice. Everyone's comfortable here?
Yeah.
Nice. So let me do another one. This one's okay. This is horrible, actually. Yeah, 4 times 7 is 28, right? So I can see this downstairs factors. So let's do this one. I've got the function. Let me take a picture of it. Now all of a sudden they switch to f of x. It doesn't matter. I usually just use f of x. I don't like using r much because I like using that letter r for real numbers, right? But we got to be careful to use a bold r. So this is homework 17, number 3. And I've got the function f of x equals 6x times x minus 1 over 4x squared minus 27x minus 7. So I see that the top is already factored, which is nice. But I want to be able to see this whole thing as standard form and factored form and then reduced form. So I think I want to distribute upstairs here 6x squared minus 6x all over 4x squared minus 27x minus 7. So that's my standard form. And remember, I'm going to wrap the new multi-term numerators and denominators before I go to my calculator. So this is my standard form. I want to factor too. I want a factored form. This one I can factor without doing any synthetic division. But if you want to, you can use synthetic division. I already got the numerator factored. I need this denominator factored, right, into this. And I know it factors because what? 4 times negative 7 is negative 28. And the factors of negative 28 are 1 and 28, or 28 and 1. And I want them to add to negative 27. So I need a positive 1 and a negative 28. Right? So this is just like factoring in 8th or 9th grade, or if you took Math 50 last semester, you did all this factoring. And you're going to show me your factoring on the test. Don't just magically have things factored. Right? So I want to split the middle term on this. Right? So I'm factoring over here. Split the middle term. Don't do guess and check. I hate guess and check. I'll take points off if you guess and check. So I'm going to do 4x squared minus 28x plus 1x minus 7. And factor by grouping. I can take a 4x out and I get x minus 7. And then I can take a negative 1 out and I get, positive 1 out, and I get an x minus 7. So I get x minus 7 times 4x plus 1. Is that okay with everyone? Thank you, Paris. Anyone else? 4, 8, 12, 16, 20. 3 students missing. Michelle's there. Good. Hiruz is there. Nice.
You said on the test you want us to see a factorial.
Yes.
We have to show all the steps how we got.
Yes.
Okay.
You could do it with synthetic. You could even do this one with quadratic formula if you really had to. But this is the way you should have been taught. And I know the way that in Math 50 they would teach you, and the way that anyone would teach factoring when you have quadratic with a leading coefficient other than 1, right? This is a process. Split the middle term, factor by grouping. So now I got my factored form, right? I've got my factored form. Does anything reduce? Does anything cancel out here? No, but that's what we're trying to do. We're trying to reduce the function as much as we can, but we really, before we reduce, we got to be thinking of the domain. So we know x equals 7 is no good, and x equals negative 1/4 is no good, right? Do you agree with me there? So I take my downstairs denominators and set them, factors, and set them equal to 0, because those can't be in the domain, right? I can't have the denominator equal to 0. So what's my domain now? It's minus infinity to negative 1/4 union negative 1/4 to 7 union 7 to infinity. Right, I've got two pieces there that can't happen. Two x values that make my denominator 0, which is bad. And so that means I know vertical asymptotes, right? Vertical asymptotes will happen at x equals 7 and x equals minus 1/4. I've got intercepts of x equals 0 and x equals 1, right? So I've got intercepts of 0, 0, and 1, 0. I'm just finding out, right, where the graph crosses the axis. Okay. So and the hint is there that the numerator equals 0, right? What's my long run behavior? And I want to use my my standard form. So f of x equals 6x squared minus 6x over 4x squared minus 27x minus 7. As x goes to infinity, I only think of the mother functions, 6x squared over 4x squared, which becomes 6 over 4, or 3/2. So I'm getting a horizontal asymptote of 3/2. So the HA, horizontal asymptote, is y equals 3/2. I'm doing, by the way, I'm teaching 4.4 and 4.5 all at once here. So I'm just teaching you everything you need to know about rational functions. And then, it's a little bit, it could be overwhelming. It could be quite overwhelming. You just have to practice and then try and remember that whole list I gave you at the beginning.
Why did 6x squared become minus 6x become 6x squared?
Yeah, so it's 6x squared minus 6x. So if x is $1 million, and I'm going to teach this to you like Dave Chappelle doing Rick James imitation, okay? So if I've got x is $1 million and I have 6x squared, okay, that's $1 million is 6 zeros. X squared is 12 zeros, okay? So do I care about losing $6 million if I've got that much money? No. And so the whole thing is, it's like, I'm rich, bitch. It's Dave Chappelle doing Rick James. If you just think of that leading term, all of those other terms are insignificant when you're thinking about millions and billions and trillions and godzillions of dollars. So in the long run, we all become our parents. So I'm taking the mother function of the numerator and mother function of the denominator and reduce it, and that will give me a horizontal asymptote. You'll see it also will give me an oblique later. It's strange. But again, what am I missing? The only thing I'm missing is short run behavior, so I'll do that in a second. I hate this one for short run behavior, but it's Math Excel. It's not as smart as, it doesn't pick the problems as smart as I would pick the problems. So here, y equals 6, and I can do it this way. I can do 6x squared minus 6x, and then I can highlight everything and then do divide. So that's like this is me wrapping them in parentheses. And then I forget already, was it 4x squared minus 27x? Is that right? And then I forget, minus 7? What is it? Yeah, minus 7, right? So, what did we find? We had intercepts of 0, 0, of 1, 0. Oops. We had vertical asymptotes of x equals negative 1/4. And you can see that blue line going up, the purple graph doesn't touch that at all. And x equals 7, right? Where's my x equals 7? Over there. Oh, look at how much more of that graph is there. So again, the purple graph is our original graph. And then we had a horizontal asymptote of 3/2, y equals 3/2. And so there's my horizontal asymptote. So it says in the long run, the purple graph will never cross that line. Okay? In the short run, it can. Okay? In the long run, you can't cross a horizontal asymptote, but in the short run, you can. So you can see it does cross it here, right? But we only really care about what happens at infinity and negative infinity. Now, the only thing I didn't find is short run behavior. But I want you to look at the two pieces of my domain that are trouble. And I want you to look at the purple graph here, right? If you look at the purple graph here, can you see my mouse moving there? Can you see my mouse? Where's my mouse? Damn it. Where's my mouse? There it is. Can you see my mouse moving on the page?
Yes.
Yeah.
Okay. So look at that and this. You can see 1 over x. This looks like the mother function 1 over x. And it's the opposite here. You see them switched. You see the up part and you see the down part. And so I'm going to show you that the short run behavior at 7 is going to give me a mother function of 1 over x. And at minus 1/4, it's going to give me a mother function of negative 1 over x. So short run. I'll just do at x equals 7. So at x equals 7, I'm going to use my factored form here. I got f of 7 equals 6 times 7 times 7 minus 1 times x minus 7 times 4 times 7 plus 1. So notice everything here is positive, 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 and I've left with a 1 over x. So it looks like 1 over x. At 7, it looks like a 1 over x.
I don't understand how it looks like 1 over x.
Sure. So this is some number times some positive number, some positive number. Well, it's actually what, 36 times 7? 36 times 7 is 252. And this is what, 29 times x minus 7. And so now I plugged in 7, right? My piece that's not in my domain, everywhere I could, okay, without getting a 0 downstairs. And I look at this and I say, what's the mother function? Well, there's only one x there, so it's some kind of 1 over x. Yes, it's a multiple of it. That just stretches it out, right? So but can you see the 1 over x?
Oh, okay, I think I see it now. But you don't plug it in where it would create a 0.
Exactly.
Right?
This is the short run idea. So now at 7, 1, 2, 3, 4, 5, 6, 7, I already know I have a vertical asymptote, right? And I can see the graph that I have is looking like 1 over x. There, look at the graph again. The graph is looking like 1 over x. And again, I'll try and highlight it here. There's my top half of 1 over x. There's the bottom half of 1 over x. Top half of 1 over x, bottom half, right? That positive part of 1 over x.
All right, got it. Thank you.
Yeah, it's weird. It's the first time you've seen it, I'm sure. I mean, has anyone seen this stuff before? Anybody see this? I don't think you have. It's mine. Unless you had a class with me. I don't know if you've seen it before. Okay, let's look at another problem here. The stuff starts to get dense. As we keep adding chapters, stuff gets more dense. You can't, if you let your bills pile up on your desk like I do, it gets paralyzing. You look at all that stack of bills and you go, oh my God, I can't do it. Same thing with the math work. You can't let it stack up. It's going to get paralyzing. And then you're finished. You're never going to catch up at the end. You've got to keep chipping away. You've got to be practicing. How many hours did I say a week? 15 hours, 10 to 15 hours a week. Some of you might have to do more if you have holes in your background, math background, if you can't factor, if you still have trouble using PEMDAS, right? If you can't complete the square, right, et cetera, you gotta practice, and you gotta chip away, and you gotta ask for help. It's not magically just gonna fix itself. If you're doing work for hours and hours and getting everything wrong, you need help. So instead of doing it for hours and hours, do it for 5 minutes and see if you get it right. Right? And if you get it right, great. If you get it wrong, you go to YouTube, or you look at your notes, or you look at the textbook, or you email Robert, or you go to the Learning Center. But you got to work. There's no way to skip the work, and you got to be honest with yourself. You can't lie to yourself. You can't pretend you get it. You can't pretend you're getting things right. It doesn't work that way anymore. There's usually a place in our mathematical lives where all of a sudden the stuff isn't easy anymore, and it's usually Calc 2. That's when you get to Calc 2, probably almost all of us will have go like, oh my God, what the hell is going on? And I say Calc 2 is the most difficult. I say Pre-Cal is the second most difficult because of the eclectic and the volume, right? Everything is all over the place, and it's a lot to do. So there could be a huge block for you here. All of a sudden, I could do all this math before, but now, right? So you got to practice. You got to ask for help. Let's look at another problem here. So factor. This particular one is interesting because I get this reduction. So I'm going to do this one. So let me take a picture here. I'm just taking a picture so I don't have to keep going back to the screen. So this is number 4. And my original function, I'm just going to use f, even though they used r, is 3 times the quadratic x squared minus 5x minus 14 all over 4 times the quadratic x squared minus 49. Now that's almost factored, right? But we want to see this distributed out because it's going to be a little bit easier to put this in the calculator correctly with parentheses. So minus 15x minus 30, 42. Is that right? Yeah. All divided by 4x squared minus, oh god, 4 times 49, 200, 196. Yep. So there's my standard form, right? What I would put in the calculator. And then I want also my...
Is that 42 after 15?
Yes. Yeah. 3 times 14. Am I right? 3 times 14. Yeah. 42. Yeah. And then this is my standard form. And my factored form, right, is what? 4 times x plus 7, x minus 7. Downstairs, and then upstairs, what are the factors of negative 14 that add to negative 5? It's x minus 7 and x plus 2, right? So this is my factored form. And then I can have a reduced form, right? Because these two factors will cancel, right? Now, what's important is that I'm getting my domain from the factored form, okay? Getting my domain from the factored form, graphing from my standard form, okay? And the reduced form is just so I can say it a lot easier, kind of a nickname maybe, right? So I always say that the best nickname is Nick. If your full name is Nicholas and they call you Nick, that's a nickname.
Oh my god.
Oh, I get it.
I saw someone wearing a T-shirt the other day, a construction worker, big fat belly, and it said on his shirt, "My very last hope for a smoking hot body is cremation." Just makes me laugh.
Do you come up with this, or do you?
No,
read them?
I saw the shirt. Yeah.
Are you really?
It's funny. So, what's my domain? I need to get that from my factored form. X should not be plus or minus 7. Yeah, neither. Even though it reduces. Okay. So, what's interesting here is at x equals negative 7, we have a vertical asymptote at x equals 7, we have a removable discontinuity. There is a hole. Not a hole, a hole. There's actually a hole in the graph, but you can't see it when you graph it, right? It's an interesting thing to do when you put it in the calculator, to look at what the table says at 7 and at negative 7. So,
Could you explain? Sorry, could you explain why there's a hole at 7 and not a vertical asymptote?
because our vertical asymptote definition is when the denominator is 0, when it gives me a number over 0. Okay. Now on this one they canceled out, so it's really, if I'm really looking at the nickname, I'd rather look at the nickname than look at the proper name. So I'm looking at this reduced equation, but I know the domain has to come from the original equation. So I know I can't put positive 7 in or negative 7 in. Okay? So the interesting thing that happens is so let me call this n of x, right? Nickname. What happens at n of 7 is I get 3 times 7 plus 2 over 4 times 7 plus 7. So I get 3 times 9 over 4 times 11. I get 27 over 44. So when I look at the graph at 7,